Welcome guys. In previous lecture we learn about the introduction, various types of NMR and the range of PMR while the spin state of the PMR. So we learn these things. Now in this lecture we are going to learn about the influence of the anisotropy on the chemical shift. So the compound on the left has the chain of 10 methylene group linking a paracarbon of a benzene ring. Such a bridge benzene called as a paracyclophanes. The meta-analogues are also known the structural constant of the bridging chain required the middle two methylene groups to lie over the face of the benzene ring, which is NMR shielding region. The four hydrogen atoms are the part of this display resonance signals that are more than 2 ppm higher field than the two methylene groups bonded to the edge of the ring, which is the de-shielding region. So, the 14 pi electron beach aniline on the right is an aromatic which obeys the 4n plus 2 system, and it has the same anisotropy as the benzene have. Nuclei located over the face of the ring are the shielded one. So all these protons are the shielded one proton, and those on the periphery of the ring, so those are de-shielded proton. So in previous year we learned this phenomena, which protons are shielded and which protons are de-shielded. The ring hydrogen gives the resonance signal in the range of 8 to 8.7 delta as expected from their de-shielded location. So the two propyl groups are structurally equivalent. So it is a homotopic protons and are free rotate over the face of the ring system and above and the below one. So on the average, all the propyl hydrogen are shielded with the same, these are the same with the innermost methylene being the most affected. So these inside protons are the most affected. The negative chemical shift noted here indicate that the resonance occur at the higher field than the TMS reference signal. So these protons are having a minus delta value. So it means they are fully shielded. So the value is below the TMS, and TMS is a standard we use for the plotting the graph. The remarkable characteristics of aniline is that the anti-aromatic 4n pi electron systems. So the systems are anisotropic and the opposite sense as their aromatic counterparts. A dramatic illustration of the fact is provided by the dianion derivative of the bridge aniline. This dianion formed by the addition of 2 electrons through the this 16 pi electron system. So the which is 4n pi electron system. In the NMR spectrum of the dianion, the ring hydrogen resonate at the higher field, so they are probably shielded. Then the hydrogen of the propyl group are shifted downfield, which are de-shielded. So downfield value means de-shielded and upfield value means shielded. So innermost methylene protons are give an NMR signal at the plus 22 ppm, and the signals from the adjacent methylene and the hydrogens are also have the expected large chemical shift. The compound in which two or more benzene rings are fused together were described in an earlier section. So in previous year we discussed this pattern, which is the 4n pi electron system. Such as we know the example, more than rings, more the benzene rings are attached together. There is the examples are such as naphthalene, anthracene, phenanthracene, which are which present the interesting insights into the aromaticity and reactivity. The resonance stabilization of this compound calculated from the heat of the hydrogen or the combustion is given beneath each of the structures. So in next slide we are going to see that examples. So here these compounds are resonance stabilization compound. These compounds having the resonance is stabilized and calculated from the heat of the hydrogen or the combustion. So unlike the benzene, the structure of this compound shows measurable double bond localization, which is reflected in their increased reactivity both in substitution and the addition reaction. However, in the 1H NMR spectra of these aromatic hydrocarbons do not provide much insight into the distribution of the pi electron. As expected, the naphthalene displayed two equality intense, which shows the two signals. So first one is 7.46 and the second one is the 7.83 delta ppm. So likewise the anthracene shows three signals, two equal intensity multiples, that is 7.44 delta and 7.98 delta ppm, and the signals half intense as a intensity at the 8.4 ppm. Thus, the influence of the double bond, the localization of this compound between benzene and the higher aniline stabilization cannot be disconcerned. Now we are going to learn about this new point, spin-spin coupling and spin decoupling. The spin interaction of neighboring hydrogen takes place through the covalent bond that join them. The most common bonding relation is a vicinal coupling. In this case, neighboring proton having plus 1/2 spin shift the resonance frequency of the proton being observed to the slightly higher value, that is near about 7 Hz. So it coupled at the 7 Hz frequency, and at the minus 1/2 spin, neighboring spin shift into the lower frequency. Remember that the total population of these two spin state is roughly equal, differing by only a few parts per million in strong magnetic field. If several neighboring spins are present, their effect is additive. In spectrum, this particular spectrum, the dichloroethane shows the on the right. It is clear that the 3-methyl this 3-methyl proton that are hydrogen marked as a red, which are coupled with the single methylene hydrogen. This is the single methylene hydrogen. These 3 methyl are coupled with this single methylene atoms in a manner that causes the former to appear as a doublet. So we can clearly see, because of this hydrogen, this CH3 appears as a doublet. So and later this CH is appeared as a quartet because of this 3 neighboring proton. The light gray arrow that points to the unpredictable shift. So this is the unpredictable shifts. So when we discuss about the statistical figure, so the statistical distribution of the spins within the each set explains both the n+1 rule and the relative easily deduced from the fact that it is must have one of the possible spins. So the interaction of these two spins with the nuclei under the observation leads to the doublet located at the expected chemical shift, that is the 2.06 delta ppm. So the corresponding action of the 3 proton of methylene group required the more detailed analysis. In the display, the interaction of 4 possible arrays of their spins shows that the mixed spin state are 3 times as possible as the all plus one half as well as the all minus one half spin state corrections. So consequently, we know that we expect 4 signals above the chemical shift and 2 below it. So the spin analysis also suggests that the intensity ratio of these signals will be 1 as to 3 as to 3 as to 1. So clearly we can see the ratio of these peaks 1 as to 3 as to 3 as to 1. The line of separation in splitting pattern are measured in hertz, and the characteristic of the efficiency of the spin interaction they are referred as the coupling constant symbol J. So in next slide we are going to learn about the coupling constant. In above example, the common coupling constant is a 6 hertz. So these protons are coupled by 6 hertz coupling. So the simple way of estimation of relative intensity of line in first order coupling pattern, and it shows on the this multiplicity pattern shown in next slide. So this array of number is known as the Pascal's triangle. So this is the Pascal's triangle, and it is easily extended to the predicted at a higher multiplicity. So here we can see the different multiplicity: singlet, doublet, triplet, quartet, quintet. The number appearing at a given site in the sum of the numbers linked to the from above by the light blue lines. Thus the center number of the 5 quintet value is the 3 plus 3 is equal to 6. Of course, this complete analysis of the spin distribution are shown for the case 1,1 dichloroethane. It leads to the same relative intensities. So previously term is a coupling constant. So now we are going to learn about or the briefly describe about the coupling constant. So the coupling constant are the independent of the external magnetic field, and it reflects unique spin interaction characteristic of the coupling set of the nuclei in the specific structure. As the noted earlier, coupling constant may vary from fraction of the hertz to the nearly 20 hertz. So the coupling constant range is between 1 hertz to the from 1 hertz to the 20 hertz. Important factor being nature and the spatial orientation of the bonds joining the coupled nuclei. In simple and freely rotating alkane units such as the CH3CH2 and the next one is the CH2Y CH3X. So these are nothing but the alkyl halide. The coupling constant reflect and the average of all significant conformers, and usually lies in the range between 6 to 8 hertz. This conformation mobility may be restricted by incorporating the carbon atom in a rigid ring, and in this way influence of the dihedral orientation of the coupled hydrogen may be studied. The structure of cis and trans 4 tertiary butyl 1 chlorocyclohexane shows above illustration. So this shows above illustration how the coupling constant change with the dihedral angle, that is theta, between coupling hydrogen. The inductive effect of chlorine shift the resonance frequency of the red color. These are red color hydrogens in the molecule. the red colored hydrogen at the lower field, that is 4 delta, and allowing it to be the studied apart from the other hydrogen in the molecule. The preferred equatorial orientation of the tertiary butyl group hold the 6-member ring in the chair conformation despite it drawing. In the trans isomer, this is the fix, and the red hydrogen here, the red hydrogens in an axial orientation, whereas the cis isomer is a equatorial. The listed value for the dihedral angles and the corresponding decoupling constant suggest the relationship which has been confirmed and clarified by the numerous experiments. The relationship is expressed by the Karplus equation. So, in next slide we are going to see the Karplus graph. So, this is the Karplus graph and this is the Karplus equation. The geminal coupling are most commonly observed in a cyclic structure, but are also evident when methylene groups are having a stereoisomeric hydrogen, and the example illustrating that is the geminal coupling. So now we are going to learn about the spin decoupling. So previously discussed point, that is spin decoupling. We have noted that the rapidly exchanging hydroxy hydrogen are not a spin coupled to the adjacent CH groups. So this is the reason should be the clear. As each exchange occur, there will be an equal chance to the new proton having plus or minus 1 half spin. Over time, therefore, the hydroxyl hydrogen behaves through the rapidly changing its spin, and the adjacent nuclei see only the zero spin average from it. If you could cause the other proton in the molecule to undergo similar spin averaging, their spin coupling influence on the adjacent nuclei would cease. Some NMR experiments are possible, and this technique is called as a spin decoupling. So here we clearly see that the adjacent proton has hide, so the multiplicity will be changed. Here for example, this hydrogen will be spinly decoupled, then this CH3 will give the signal singlet. There is no adjacent hydrogen, so that's why this CH3 will appear as a singlet. While we hide this 3 hydrogen, we hide this CH3 proton, then same way this CH will show the singlet. So the quartet will change from the singlet due to the spin decoupling. When a set of the nuclei is irradiated with the strong RF energy and its characteristic Larmor frequency, spin saturation and rapid interconversion of the spin states occurs. Neighboring nuclei with the different Larmor frequency are no longer influenced by specific long-lived spin. So, spin signals are splitting of the neighbor vanishes. The following spectrum of 1-nitropene may be used to the illustration of this technique. So here the NMR plot where we can see the 3 distinct set of the hydrogen in the molecule generate 3 resonance signals. There is 2R triplet and the broad sextet. Carefully tuned the decoupling signal may be broadcasted into the sample while the remaining spectrum is scanned. The region of decoupling signal is occur, but the resonance signal which are hidden. So the resonance signal more than 60 Hz are away may be still be seen. So In this example, we clearly see the nuclei being the decoupled and the nuclei being observed by spectrometer are same kind for the both proton. We call this phenomena as a homonuclear decoupling, and it is also possible to decouple different kind of the nuclei. For example, the compound having both hydrogen and the fluorine as a part of its molecular composition may exhibit spin coupling between their nuclei, and one may be decoupled while the other is observed. This term is a heteronuclear coupling. So heteronuclear coupling is very important in 13C NMR, which we discussed in the C13 spectral part.